In this video, I focus very simply on linear wave theory. Let's start. To explain linear wave theory or airy wave theory using zeta for surface elevation or surface up and down around mean sea level, this constant line, we treat the ocean as an idealized fluid. The goal is to find a mathematical expression for the velocity potential function phi, which then allows us to calculate the pressure velocity at any point in the water column between constant seabed and mean sea level. By idealized, here I mean a two-dimensional wave, say in xz plane, and the fluid is inviscid, no friction, incompressible, irrotational, constant depth, and finally these waves are small amplitude with respect to wavelength. Based on these assumptions, we can define the velocity potential function phi. Based on the stated assumptions, we define the velocity potential function phi. In that regard, the horizontal and vertical velocity components u and w can be obtained directly from the potential function. In the xz plane, the horizontal velocity component u is given by the derivative of phi with respect to x, while the vertical velocity component w is given by the derivative of phi with respect to z. The velocity potential must satisfy the continuity equation for incompressible flow. This leads to Laplace equation, as shown here. To solve this equation, to obtain and estimate phi, appropriate boundary conditions are required. These include both kinematic and dynamic boundary conditions at the mean sea level, as well as a boundary condition at the flat seabed. It should be noted that this formulation is valid within the framework of linear wave theory, assuming a domain extending between a flat seabed and the mean sea level. Let's begin without going into further detail with kinematic boundary conditions, which describe the motion of fluid particles both at the seabed and at the free surface. At the seabed, there can be no vertical flow through the boundary. This implies that the vertical velocity must vanish, which leads to the condition that the vertical derivative of the velocity potential is zero. At the free surface, fluid particles must remain on the surface. Therefore, the vertical velocity is directly related to the time derivative of surface elevation zeta. In general, this relationship can be written as a kinematic condition linking the motion of the surface to the flow beneath it. Within the framework of linear wave theory, and assuming small amplitude waves, this condition can be simplified. Higher order terms become negligible, and the kinematic boundary condition at the surface reduces to this expression, which shows that the vertical gradient of the velocity potential at the free surface is equal to the time derivative of the surface elevation. From this relation, we see that the surface elevation zeta can be directly linked to and represented through the velocity potential phi. The dynamic boundary condition at the free surface is related to balance of forces, or equivalently the pressure. It is based on Bernoulli principle, which provides a relationship between velocity and pressure. At the free surface, the pressure is equal to the atmospheric pressure, and Bernoulli principle can be expressed in terms of the velocity potential as shown in this relationship. In this formulation, the time derivative of phi is related to the velocity components through kinematic energy terms, while the term gz zeta represent the hydrostatic pressure associated with the surface elevation zeta. Within the framework of linear wave theory, this equation is simplified by neglecting the nonlinear velocity terms, the quadratic terms. This leads to a linearized form of the dynamic boundary condition. This expression allows us to directly relate the surface elevation zeta to the velocity potential phi at the mean sea level. Based on the simplified boundary condition, the solution of Laplace equation can be obtained analytically and is expressed as follows. From the velocity potential phi, we can determine surface key physical quantities, including the dynamic pressure, the horizontal velocity and vertical velocity components, and the surface elevation.